So Andrea is a astrophysicist, a very well known. The Pluto code is one of the most well known astrophysical PhD, hydro, and beyond these codes, as you have experience with. And Andrea is a professor at University of Torino. So I won't really go into details of his accomplishments and history and so on. You can read that up. So we'll just get started with this talk. Over to you, Andrea.
Okay, well, thank you very much, Pratik. It's an honor for me to be here, and I'm so glad that there are so many people involved in MHD and also in using the code, using Pluto, which is something I've been working on for several years now. So today's talk is going to be quite general on good HPC practices, life as a computational astrophysicist, Pluto code, and so on. Okay, so before we begin, I just want to give you a short intro, okay, of what's the outline of the talk. So I'm going to start with something that you may already know, probably, which is astrophysical plasmas, what is the evidence and the theoretical background. Then I will move to numerical computation. I will give you a practical example, especially for those of you who are not used or do not understand exactly how in practice numerical computation can be performed. Then I will introduce the Pluto code, the design, general philosophy, and then I will switch to, for those of you who are taking a master or beginning the PhD, the 3 rules to become a good computational astrophysicist based on my personal experience. And finally, I will conclude with the plans for the future. So, but let's start. Okay, part 1, astrophysical plasmas, evidence and theoretical background. So probably it's needless to say that more than 99.9% of the matter in the universe exists in the form of a plasma. A plasma is a ionized gas where charged particles can interact through electromagnetic forces, so electric and magnetic fields. There are several examples that I can name, for example, stars, nebulae, galaxies, supernovae, interstellar or intergalactic medium, jets, accretion disk, and so on. So one thing you must keep in mind at all times is that our knowledge is always limited by what we can actually observe. Okay, so everything we know from this object is coming from the light, from the photons that we received on Earth or on satellites. Unfortunately, astrophysical plasma conditions are very diverse between. So if you take a look at this table, this is a very approximate table giving you an idea on what is the range of length, density, temperature, velocity, and magnetic fields depending on the object at hand. Stellar interiors, you go from 10 to the 10 to the 12 centimeter, but if you go down to jet in AGN, then your spatial scales become much, much wider than that, and you hit a 10 to 24 centimeter. And the same it goes for the density, ranging from very large density inside stellar interiors to very low density in the extragalactic medium. Similarly, for temperature velocity, that can go from a few 100 kilometers to the speed of light, and also for magnetic fields. Now, when you do astrophysics, you have to keep in mind that most of the times flows will be compressible, magnetized, supersonically, and possibly relativistic. There are also several other ingredients that may come, such as cooling, radiation, gravity, non-inertial effects, a complex equation of state, stiff reaction network, and so on. So as you can see, inside astrophysics, there is a lot of physical ingredient may come into play. And this is actually the real big problem in today astrophysics, the major challenge, scale separation, okay? So it's impossible to have a scheme, a numerical method, or even a theory that can cover from kinetic to fluid, from small scale to large scale. So depending on the scale you want to investigate, you may prefer one method over the other because there is a huge gap that stretches from theory to a clear interpretation of the observation of high energy astrophysical sources. So that's why currently our computational modeling is also very much fragmented under different scale applicability. just to give you an idea, if you study, for example, a system like this, which some of you may know, is just an accretion disk, okay, maybe around a black hole with two jets outflowing from the center into opposite direction. Now you can start this at the turbulent scale, which is just by considering an extremely small patch inside the accretion disk, or you can study the whole accretion disk, but then you will have to sacrifice turbulent because there is no way you can resolve both scales. Or you can study just the jet propagation without studying the disk. So as you can see, it's very difficult and very hard to consider the whole problem in one single computation or even one single model, okay? Because the same astrophysical object can be observed at different scale, different lengths, and different also radio or optical different visible or, sorry, signal length. So just to give you another idea, this is a different view of the same problem. When you study a jet, you may concentrate on the launching region, the confinement collimation region, or the propagation region. They are all different scales, okay, that differ by several order of magnitude, from astronomical unit up to megaparsec scale. So from 10 to the 13 to 10 to the 22. Now, let me show you something you may already have covered during this course. So I'll probably go fast on this, but if you want to make me question, I'm available. So here is a hourglass, where on the top we have the microscopic scale, the kinetic description, and then we can go down up to the fluid macroscopic description. And depending on the scale model, we may choose one theoretical description or another, like I said before. For example, if I decide to stay at the small scale, I mean a scale of about a few thousand kilometers on a temporal range of let's say 100 seconds or so, then I can use the kinetic description, which is definitely the best way to describe a plasma, but it is limited to those scales. And then you can use a kinetic description and a particle in cell code, which is applicable for those scales. However, if you wish to study larger scale, you need to sacrifice some of the information by doing some averaging technique that will bring you from peak up to hybrid kinetic, ion scale. So we already are losing some electron physics in order to capture larger and to describe larger scale range. And then you can cover hybrid kinetic models that stretch up to the astronomical unit on a time scale of a few hours. If you are not happy with that, because you need to describe even larger system, you can keep going in averaging down the property of the system, and then you hit the two fluid description, and you start using the fluid model, one fluid, and eventually MHD. Okay, so at the microscopic scale, you are essentially here, and you solve Vlasov equation, okay, using, for example, a particle in cell approach, which is essentially a finite element approach to the previous equation. Okay, the distribution function is given by the superposition of several elements, which we call the superparticles. Now, each element represents a large number of physical particles that are near each other in phase space. I think you already covered this from the program. Now, peak is the most consistent approach. However, it's tied to the electron skin depth. It means that the basic scale is about 10 to the 5, 10 to the 6 centimeter, and you cannot go much farther than that because you must resolve the electron scale. However, if you start sacrificing some of the physics, you can extend to wider range, and then you need to fluid description, which is essentially appropriate for a two-temperature plasma. It is obtained by averaging the distribution function over momentum space. Thus, it is only valid if you consider lengths that are much larger than the mean free path between particles. From the previous equation to this one, you are essentially dealing with partial differential equation. As you can see, each equation comes in pairs. There is one for the ion, one for the electron, one momentum equation for the ion, one for the electron, and the same for energy. Everything is, of course, coupled to the Maxwell equation, because you see the plasma is exactly a complicated system where particle generates the fields, but the field then affect back the particle in a loop. So it's the ensemble of these two things that must be resolved at all times. If you keep averaging down in order to reduce the complexity and going to larger scales, then you end up having the one fluid and MHD. Now, the one fluid description is based on the averaging ions and electrons equation together, okay? And then you can deduce magnetohydrodynamics by making the further following assumption. First of all, you are working in a regime with very low frequency. So that means that any frequency you have will be, and must be less than the plasma frequency, the cyclotron frequency, and the collision frequency. And for the scales, the opposite is true. Length must be very large in order to average, to use the fluid description. So you must be on scale larger than the skin depth. The skin depth is defined by the ratio between the speed of light and the plasma frequency, the gyro radius, and the mean free path. Okay, so in MHD, essentially we ignore all the electron effects, okay, and finite Larmor radius effect. The derivation of the equation is usually done under condition of strong collisionality and local thermodynamic equilibrium and isotropy. All the three assumptions may be questioned, of course, but let's state it in this way. MHD is a simple theory, and it is the simplest theory that we can start from. If you understand MHD, it's good. You are not happy with that, you can still go back and reincorporate some of the effect that you neglected before, okay? But at the moment, MHD is our simplest theory, and these are the equation of MHD. You can see the continuity equation, the equation of motion, which is essentially the second law of dynamic, like F equal ma, but for a fluid, of course. So this is the Lagrangian derivative, and you have two forces, a pressure gradient and Lorentz force. Then you can complement that with the first law of thermodynamics and Faraday's law. One important thing, these relations are complemented by Ampere's law, which in MHD loses the displacement current, Ohm's law, which simply says that the electric field is zero in the rest frame, and therefore in the moving frame it will be minus U cross B, divergence-free condition, and the closure for the equation of state, of course. We need a relation that puts together internal energy, pressure, and density. However, this is not the usual form that numerical method use to solve the MHD equation. Another form, which is totally equivalent, is preferred. And this is called the conservation equation. In a conservative form, you put all the equation in this framework, essentially. Temporal derivative of something plus the divergence of a flux equal to zero. This is the best way to capture global integral conservation quantities such as density, momentum, energy, and magnetic field. Now, let me just say that MHD is suitable for describing plasma at large scales. That's a fact. It's a good first approximation to much of the physics, even when some of the conditions are not met. It allows you to draw some intuitive conclusion concerning plasma behavior without resorting to the full equation in detail. And very important also that these ideal equations are hyperbolic conservation law. You will see in a minute why we call them conservation law. Now, you can, of course, take a step further or backward, depending if you want to recover some of the missing effect, and then you consider non-ideal MHD. Then you can say, well, I need more physics to come into play, for example, viscosity. Then I will add this red divergence term on the right side of my momentum equation. Tau is the viscosity stress tensor. Or I may want to include, for example, thermal conduction or resistivity, Okay, so in this way, I'm leaving in black hyperbolic term, I'm leaving in red terms that are describing dissipation physics, so second order parabolic equation, and in blue, I'm describing point local source term, which usually require explicit or implicit ODA time stepping. But then the question, why do we need numerical simulation? I mean, why can't we just use paper and pen and become a good astrophysicist? Well, probably the answer is pretty obvious to me, but not to everybody. So let me just say that the exact solution in MHD are possible only if you have very restrictive assumptions, such as stationarity, it means everything is time independent, self-similarity, spherical symmetry, or slab symmetry, or something like that. Or you can solve the equation in the regime of small perturbation, but that will be only valid for short times. In general, if you want to solve the problem in its totality or to do more than that, you need to solve the full nonlinear time-dependent system, and that can only be solved by means of numerical simulation. That's really the only tool that we have available to carry such a task. Now, in fluid dynamics, you deal 90% of the time with the grid-based fluid approach using either finite volume or finite difference methods. Now, in this approach, the fluid variables are discretized on a special grid, which can be static or adaptive, adaptive meaning that it can change in time, and these fluid variables are then evolved in time. The numerical solution, however, of this hyperbolic PD must also consider the possibility of discontinuous waves, such as shocks, contact wave, or rotational discontinuity. And for this reason, we will use shock capturing or Godunov type scheme. Before I go into the detail, so I cannot see probably if you raise your hand, but how many of you have already carried a numerical simulation, even a simple one? Okay, take your hand down. Now raise your hand if you have never done such a thing. Oh, okay, nobody. Well, I mean, at least I cannot see many people. So therefore, I can probably skip on this, but let me just warm up the audience in the following way. Suppose we want to study Rayleigh-Taylor unstable flow, okay? So you know that the finger that you typically observe in a supernova remnant are likely to be the final result of a Rayleigh-Taylor instability, because the contact wave that moves away is slowed down, and therefore if you sit on the contact wave, it's like being in a non-inertial frame where you feel a fictitious force pointing outward. But that's the same thing as simulating a Rayleigh-Taylor environment with heavier fluid on top of a light fluid. Now, of course, you cannot, you don't want to begin by studying the whole system, so you will concentrate on a small patch of this system. Let's say I'm considering this white box that you see here. Now, on that white box, I will set my number of zone, computational cell, and then I will need to further prescribe an initial condition. For example, I may use that the density is 2 where the fluid is yellow and 1 where the fluid is blue, and gravity will be assumed downward. I'm calling gravity, but in the example I showed before, there is no real gravity. It's just I'm using the letter G, but in the case of a supernova remnant, it means the non-inertial acceleration that you feel pointing outward. It's the same kind of acceleration you feel on your car when you all of a sudden brake, okay? Then your body will feel transported in front of you. Now, how do I set the initial condition? Nominally, when I want to address a fluid instability, it's always a good idea to start from an equilibrium. I want to have an equilibrium condition to start from. So in this case, the density is a jump, but the pressure is continuous, so that my pressure will exactly balance gravity. Then there is another important aspect to consider in a numerical simulation, always, boundary conditions. The boundary condition not necessarily have to mimic a real system, but they must be chosen so as how can I say this, not to sacrifice some important they must preserve somehow some properties such as energy transport or global conservation. For example, in this system, if I choose periodic condition on the left and on the right and reflective on top, then I'm sure that the total energy, mass and momentum of the system can never escape from the system, because a reflective condition is like a wall, and the periodic condition means that everything that goes out on the right is gonna come back on the left. So this condition, for example, ensures that I'm conserving energy. So my net balance will be 0. Okay, now once I'm ready, I can start a simulation. Okay, and I can study, for example, the evolution of these fingers, which will closely grow by merging and forming larger fingers. How many in the audience are familiar with the physics of the Rayleigh-Taylor instability? Okay, so you all studied that, right? So you know that this finger, so you know that the growth rate is larger for small wavelength, therefore for large K, and it is actually smaller the opposite way. But now I have a question, a more complicated question. Let's see if somebody can answer. How many modes can I see in my box? Can I see all of them, all the possible Ks from 0 to infinity, or only some of them? I don't know if you have a microphone and somebody can answer this question. That will be interesting to know.
Yeah. So yeah.
Some of them, because the size of the modes would be constrained by the size of the box that you're simulating.
Exactly. That's a very good question. Indeed, you have to keep in mind that inside your box, you can only fit multiple of your, well, submultiple of your main length. So the largest wavelength you can fit is L. And then you can fit L over 2, L over 4, L over 8, and so on until you hit delta X. Delta X is your spatial resolution. The larger, the more wavelength you can fit. But definitely you cannot fit wavelength larger than your domain. Okay, now let's see how the Pluto code was designed, because it is exactly intended to study these and many, many other systems. Now, I started writing Pluto approximately in 2003 during my PhD in Chicago, and then I kept developing the code ever since. Now, Pluto is a modular parallel code whose aim is that of providing multi-physics and multi-algorithm framework for solving the equation of gas and plasma dynamics in astrophysics. And for that reason, it will target multidimensional compressible flows with large Mach numbers. It can deal with Euler or Navier-Stokes equation, MHD, and also the corresponding relativistic extension, relativistic MHD and relativistic hydro. Recently, we have added to the code a new module that allows you to describe particles also. The code is freely distributed under this link, and the current version now is 4.4 patch 2. Some people sitting in the audience have and are actively participating in this development, Bhargav, for example, and Dipanjan. Now, Pluto has been always designed to be the kind of code that you can use on your laptop, or you can use on a huge supercomputer, okay? Because I always believe that numerical computation, I mean, nice idea will start always on your laptop, on your local desktop. And that's the beauty of an idea. It's simple. Then you can go further and say, okay, I need more resolution. I want to move my problem in 3D. I want to introduce whatever effect I need. Then I will move to the supercluster. But the code must be able to run even on a small computer. Having said that, however, we have tested the code also in parallel to very large processor. We hit more than 200,000 processor with very nice scaling. Now, Pluto comes into flavor, static, single fixed grid, or adaptive mesh refinement module or facility, which allows multiple redefined block structure nested grids to be formed to follow your solution. But I'm not going to talk about adaptive mesh refinement in this talk. Okay, I want to focus instead on the code design and philosophy, which is a nice one in my opinion, and a winning one also. So Pluto has been designed to study system conservation law. So whatever the system is, it doesn't matter if I'm talking about Euler equation or MHD or relativistic MHD, your equation always has a form like this. Du over dt, U is an array of conserved quantity, plus divergence of F. F is a tensor, comprises all the flux, and S is a source term. Now, it's nice to split, for numerical reason, which I will explain shortly. It's nice to split the flux into two contributions. One is called F hip, which means hyperbolic, and that is related to wave propagation. And F par. F par accounts for the parabolic or diffusive fluxes, and it describes dissipation physics only. Now, the base block is the following one, because you can show by using Gauss theorem, you can integrate the following continuous relation to make it become a discrete relation. However, this is an exact process, not a discretization. Although I use the word discrete, it's just the continuous equation transformed into a discrete relation, which is exactly called the finite volume building block of the method. Now, in other words, let me comment on this form. Now, what this form tells you is that the average of a quantity, okay, let's say, suppose U is density or energy or momentum, can change only because you have a net flux through the boundary. Okay, so U density will change if there is an outward flux larger than an inward flux. Okay, and this is an exact relation. It guarantees that you will conserve mass, energy, momentum. Nothing is created or destroyed. It gives you an integral representation of the original PD, and therefore it is more exact because nature doesn't go by derivatives, it goes by integrals. And the integral form, therefore, is able also to capture a shock. This is not difficult to understand if you think that a discontinuity has no derivative, but can be integrated. And that's why the conservation law is better than the differential form. Okay? So the integral form indeed does not make use of any partial derivatives. So in that sense, it's perfect if you want to capture shocks or discontinuity in general. Now, then you will say, well, if you have an exact relation, it means that we can solve exactly. Well, no, unfortunately, it's not that easy because the approximation comes in when you compute the flux. Indeed, the flux is a temporal average of the solution at the interface. Since you don't know the solution in time, it means you cannot compute the flux. So the previous relation is actually useless unless you find a way to approximate the flux in time. And that's exactly the concept behind this problem. But the way you compute the flux in time depends on whether the flux is hyperbolic or parabolic. Because if it is hyperbolic, we need to use one method. If it is parabolic, a different method. Now, if the flux is hyperbolic, we use the Riemann solver concept. Okay, this is an approach that dates back to the work of Godunov in 1961. Godunov was thinking, well, if I consider that at an interface, the solution is always discontinuous, all right, so the solution is always piecewise discontinuous, then what I need to do is to ask the question, okay, given two discontinuous state at a given interface at the time level 0, okay, what is the solution next in time? Graphically speaking, this is the Riemann problem. Left state, right state, this is the condition at t equals 0. And the vertical axis represents your cell interface. What happens next? Well, the answer is this. The discontinuity breaks and you will generate two intermediate waves. Well, two because this system has only 3 waves, but you can have more than 3 waves. You can have 7 waves, okay? And then you will generate more intermediate states. Now, all you need here is the flux, which is the solution at the axis. A graphical representation of a Riemann problem is the following. Now you can see what we call a shock tube, okay, where we have a initial jump in density and pressure, and in the bottom you can see the evolution of the three waves. Now these three waves are a left rarefaction, a middle contact, and a right going shock. The left rarefaction can be seen in the space-time diagram as the line between the violet and the blue. The contact wave is the line separating the blue from the green, and the shock is separating essentially is the line separating the green from the black. This is the case for the Euler equation. But if you move further to MHD, relativistic MHD, well, the situation complicates, because now you can have also some other intermediate waves. You can have fast waves, Alfvén wave, slow waves, and the entropy waves. All of them, except of the entropy mode, they always come in pairs. So there is always a pair of fast waves, Alfvén or slow. And in turn, each wave can be either a shock or a rarefaction. Now, the problem is mathematically difficult to solve, although it can be solved exactly. However, people never use that approach because it's extremely time consuming. Anyway, what comes out of this is a similar pattern, but now you will observe many more lines separating more waves, okay? Because you have 7 waves. And this is, for example, a MHD shock tube. As I was saying, nobody really solves the equation of MHD using exact solver, well, almost anybody, but people prefer usually an approximated approach. Then you can use either linearized Riemann solver, like the raw Riemann solver, which assumes that you can locally freeze your system at the interface and then study the evolution of waves in a linear fashion. Or you can use a nonlinear solver where you actually simplify the solution by guessing, for example, the outermost speed, and then retrieving using the overall conservation properties to define the intermediate waves, okay? These are very much used, so they are typical approaches are the HLL, HLLC, HLLD solvers, solving respectively 2, 3, and 5 waves. Okay, so having said this, I can just show you what is the overall strategy of the code, of the Pluto code, but not only of Pluto, many other finite volume Godunov type code use a very similar approach. So in essence, this is how it works. You start always from the volume average of your solution. This is the basic data that everybody has at the beginning of the computation. Now, at that point, you need to perform a reconstruction operation because you want to improve your spatial accuracy. So if the red constant horizontal lines are the averages, the blue curves are your attempt to fit a polynomial in that cell by using neighbor information. That will generate piecewise polynomial data, but this polynomial will generally be discontinuous at the interface. Now, at that interface, since you have discontinuities, is the right time to apply your Riemann solver and then study all the Riemann fan propagating out of each interface. That, as I said before, it's important because it will give you the flux. Once you have the flux, then you can update your variable using a simple time-stepping algorithm, for example, a Runge-Kutta algorithm, and then you can evolve your solution at the next time level. And then you keep repeating. So all the code is always based on the sequence of these 3 steps. One comment, however, I should say about the diffusion flux. Now, when you include extra terms such as viscosity, resistivity, ambipolar diffusion, or thermal conduction, this cannot be treated in a Godunov type way for a very simple reason, because they do not involve wave propagation. If you study them, indeed, they will bring to an infinite propagation speed. okay, because they belong to realm of parabolic equation. In this case, you do not require upwinding, so discretization does not require upwinding. Everybody here in the audience is familiar with the concept of upwind?
Yeah. Yes,
Yeah, okay, perfect. So in this case, you can discretize this term using central differences. This is perfectly okay? Because these are parabolic terms, there is no wave propagation associated with them. Well, not in the sense of a linear perturbation theory. Now, having said that, I can say that Pluto is always expanding. At the moment, it allows you to choose between different physics modules. There is also a Poisson solver in development phase. Lagrangian particle is not more development, actually. It should be put separately. Also important, the modularity of the code extends not just to the physics, but also to the algorithms, because you can go from second order scheme to higher order schemes using different solver, different way to control your divergence of B condition, etc. Pluto is being distributed worldwide. We received more or less about 500, slightly more than 500 downloads per year. So this is the distribution map of Pluto 4.3 and 4.4. It is, however, updated to 2021. We need a further update, but it's not easy to generate these maps. Okay, so is there any question for this first part? Because then now I want to move to the 3 rules.
I don't see any questions at this point. You can continue.
Okay, let me continue then. So the 3 rules to become a good computational astrophysicist with a nice vignette. So there is the student asking the professor, I'm not a very good programmer, Professor Smith. That's okay. Part of getting your PhD is learning to learn whatever you need to learn to make your research work. It's about stepping out of your comfort zone and learning new skills. Also, you are cheaper than hiring a real programmer. So that's essentially how my life began in 2003 in Chicago, more or less. Well, the dialogue didn't exactly go that way, but that was the concept. So becoming a computational astrophysicist is, well, it requires you some effort, okay? I don't want to say the word difficult, because if you like the subject, it's not going to be difficult, but it's a long way. Now, rule number 1, improve your knowledge in fluid dynamics and plasma physics. If you don't respect this rule, it's useless to follow the other 2. So it's very important. So the first rule is about theory, and it is a necessary step in the process. Without this sort of knowledge, you will never be able to interpret, understand your simulation results and place them against an astrophysical background. So take a course in fluid dynamics and plasma physics. Try to understand what are the model and theory approximation, like I said at the beginning of the talk. What are the properties of the equation? Are they hyperbolic, parabolic? What kind of mode do they support? Are there equilibria? Can I study equilibria? How stable or unstable are these equilibria? Does your system allow wave propagation? Can I perturb it and grab some information from linear perturbation theory? How can I study instabilities? What are the dissipation mechanism, etc., etc. Okay, there is a long list, but the slide stops here. So this is very important. Rule number 1. Then you can think about going to rule number 2. Make your knowledge valuable, rare, or unique. This is the way you want to be hired by somebody, okay? People that develop a particular knowledge on some specific field will become valuable to the group that need a person with that particular profile. So numerical simulation are obviously the future, because computational power is expanding, new technology are coming, so it's a good idea to invest in this kind of field, okay? You will always find a job somehow. However, becoming a successful computational astrophysics requires lots of skills from 2 different areas. One is astrophysics, and that's why you need to learn about fluid dynamics and plasma physics in particular, but also from computer science. So if you have not done so, I strongly encourage you to take as many numerical courses on methods of your preferred choice, okay? However, beware, you cannot be omniscient. You cannot learn everything, okay? Because it's just not feasible. Try to understand what kind of numerical methodology is more appropriate for you. I mean, spectral methods or finite difference, implicit equations, matrix solvers, or explicit solvers. Okay, try to give a defined preferred line to your learning curve. Okay, then you can always learn things after, but don't try to become omniscient in the first place. You will always fail, okay? Because there are many subtleties that you need to understand for every field. So try to get expertise and specialize in one particular field. Also, do possibly a lot of coding. Okay, it's good to go to a course, but to take a class in numerical methods, but always realize that a numerical method can never be assimilated on books or on slides. You need to code, 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 and code, okay? So I did countless hours of coding. Choose a language which is appropriate. Fortran, C, C++ are all very valuable programming languages, and they are all very good. Honestly, I prefer, well, personally, I prefer C or C++ because they are more modern, but also Fortran 90 is a perfectly nice programming language. Don't use Python to do numerics, however, because Python is not a programming language. Python is an interpreter. It's used for data analysis, scripting, or other purposes, but not make Python do heavy computation, okay? It's not designed that way. Rule number 3, approach computation safely. So imagine now you have acquired your background in fluid dynamics and numerical methods. Now, it's true that numerical simulation are the only viable tool to understand complex physics, but that doesn't mean that they will always give you the correct answer. Okay, why? Well, you know, then when you discretize a question, you will find, you solve it, you will find the solution to a different equation from the one that you started. Okay, that's because numerical diffusion can come into play. The discretized version is not equivalent to the continuous equation. So understanding this will guide you in discerning the limits of your model. Now, having said that, you must, when you define a problem, choose and define this problem very clearly. First comment, because I see many students doing this error. Do not use CGS units, okay? Do not say assign density using gram per centimeter cube or velocity in centimeter per second. Scale your problem to code units and make sure that, for example, your reference density is always 1 in some part of the flow, okay? For example, if you study an accretion disk, you can choose the disk density to be 1 and the interstellar or intergalactic medium immediately above or below less than 1. But don't use CGS because that will always confuse the code and run into machine error problem. Now, add one physical mechanism at a time, okay? So if you know your problem will include thermal conduction, viscosity, MHD, particles, and radiation, please don't do a simulation by including all these effects at once because you will never understand who is doing what. So define, give a priority to what physical mechanism is the most important one, okay? So from top to bottom, and then insert one after another and check the differences and the problem they may or may not eventually bring in. Ask always yourself, what are the smallest and the largest scales, and I'm talking both spatial and temporal, that you hope to resolve? I mean, is this feasible at all? I mean, because if you want to resolve, let's say, the whole galaxy describing each solar system, let me tell you, this is hopeless, okay? So numerical methods can probably cope at the best with a scale disparity of 1,000. maybe some more in the future, but you cannot definitely go beyond 10 to the 4, okay? So every scale disparity more than 10 to the 4 will not be resolved by the code. Another question, do I have enough computing power to achieve my goal? Keep in mind that let's say that you want to double the resolution. Well, keep in mind that each time you increase your resolution by a factor of r, your computation will slow down by a factor r to the d plus 1, where d is the number of dimensions. So let's say I have a fairly good result with the resolution of 100 cube. Good, I want to double. Well, but I should get ready that the computation at 200 cubed will require 16 times as much time. Okay, so if I spend 1 day to get my 100 cube simulation, I will have to spend 16 days now to get 200 twice resolved computation. Then, very important, I often see people saying, oh, that's a nice picture. I got a nice picture. Yes, but what's the physics behind the nice picture? I mean, don't stop at the nice picture. Don't trust your results blindly. How accurate are they? I mean, how can you trust that whatever your simulation outcome is correct? Okay, so there are a few ways to do this, but it's not always possible. So for example, if you have validated your method against the simpler numerical solution, reference solution, then you know at least you are solving the right equations. But that doesn't necessarily mean that your problem, which is probably more complex, will be solved correctly. One way to do it, for example, that's a necessary condition, but not a sufficient one, is however to repeat the computation by trying a different resolution. Do you get the same answer if you double the resolution? Okay, so that may prove to be a winning strategy. Okay, but always interpret your result with care and always try to understand the physics behind. For example, if I'm showing you these 3 movies, what am I seeing here? So this is a plasma column, okay, obviously becoming unstable. What am I looking at here? I have 3 different cases, 3 different evolution. What are these? Anybody knows?
Instability and stability.
Okay, so let's start from the left. What is this?
That's, I think, the sausage instability.
Sorry? I just didn't hear you very well.
I think it's the sausage instability. I'm not quite sure.
It's a Kelvin-Helmholtz instability. However, it's being 3-dimensional. You see mainly the M1 mode, because see, the physics of 3-dimensional instabilities can be very different from 2-dimensional counterpart. This is purely Kelvin-Helmholtz. And what about the second one? Oh, this is very easy to recognize.
They just said kink instability at low beta plasma.
Yes, but to be more precise, is a current-driven instability. We call it the kink instability, but kink means that you have the M1 mode, but for a current-driven configuration. And the current-driven is because current and magnetic field are parallel to each other. Okay, so in that case, you can have this helical displacement. But for example, if I counterbalance my force not with the J cross B, but with the pressure gradient, I get a completely different answer. Because in this case, I have a pressure-driven instability. They are all M1 mode, they are all kink mode, but that's a kink mode from Kelvin-Helmholtz. This is a kink mode for current-driven, and this is a kink mode for pressure-driven. Well, actually, to be honest with you, the last one is not really kink mode because the sausage instability kicks in far faster for this mode. But in principle, I have both of them, okay? So this is the explanation of what I see. You can understand better the instability if you look at them for a small amount of time where I can really see. So I have done a comparison of the growth rate with the linear theory, and I get perfect match in the linear phase. So I know what I'm talking about here, okay? So I suggest you also try to get your expertise in the same way. Always try to understand in each phase what you're looking at. Future plans for the code that I will be happy also to see some of you involved in this in the future when you become famous scientists. So what is the future of the code? Well, we have several things boiling. Definitely the most important one is GPU porting. So we are getting Pluto exascale ready. I will tell something in the next final slides. We are also invest a lot of effort in developing genuine finite volume fourth order scheme, because Pluto at the moment is only second order. Even if some of the reconstruction says PPM, parabolic, WINO, or MP5, the code remains at second order level because in several places it is assumed that the point value can be interchanged with the finite, with the average of the solution. We will also start developing a new adaptive measure refinement module for the code rather than using Chombo, mapped grids, and Lagrangian particle feedback in the future. Also, some efforts is being devoted to relativistic collisionless reconnection. But as I said, the most important part here is GPU. Pluto is currently being ported to graphic processor unit, which is a technology of the future, is one of the technology of the future. We have already carried it, well, 30–40%. We are getting speed up factors between 10 and 50, meaning that the same computation run on the CPU, on the GPU will be 10 times faster or even 50 times faster. We choose C++ and OpenSCC. So Pluto 5, GPluto, will be in C++. These required a complete rewrite of the code because understanding how GPU manage memory and data transfer between CPU and GPU is complicated. So we had to start from scratch again. In time, we will slowly port several other modules. At the moment, we have just a basic module, hydro MHD, relativistic hydro, relativistic MHD. There are no particles, but we have a student working on that. I should say that at the moment, our group has a leading role in two major HPC related projects. One is a European project called SPACE, is the acronym of Scalable Parallel Astrophysical Code for Exascale, which is a major 8 million euros budget project to get codes, astrophysical code to exascale platforms, okay? And I want to end this talk by this sentence, which was written by Attilio Ferrari, who recently passed away. He was my mentor. So the development of next generation technology holds the promise of a wealth of new, groundbreaking scientific discoveries, provided that equally advanced simulation tools are created to exploit these computational resources. For a field like astrophysics, which is largely inaccessible to laboratory experiment, the relevance of this development can hardly be overestimated. So you can find a job here for sure, okay? So that's about the end of my talk, and I'm here for questions.
Thank you, Andrea. Let's thank Andrea. And now we can have a few minutes of questions. So the space framework that you're talking about, Andrea, so how many codes are part of it, and what is the sort of big picture aim of this?
Okay, so we have selected 8 codes for the Center of Excellence. These 8 codes include Pluto, Ramses, 3 codes from GUF, from Red Solas group, so Whiskey and Bach and Phil. Then we also have a couple of codes from cosmological simulation, and I'm talking about Changa, Gasoline, and Open Gadget. And then there is one code from La Pentas group, which is IPIC3D for particle in cell simulation. So it spans more or less the 3 families of code: N-body, PIC, and grid codes. It's a COE, Center of Excellence. It began in this year, 2023, is gonna last until for 4 years, so end in the 2026, December 2026.
Hi,
So-
Andrea.
Hi.
Thanks for the nice talk. I am Vinay Kumar from ICTS Bangalore. My question is just out of curiosity, why did you name the code Pluto? Any particular reason that you have?
Okay, I think I have a backup slide on this. Just give me a second, I need to find it. Okay, I knew somebody was going to ask this question, and so this is the answer. So why did I call it Pluto? Okay, originally the name came from Disney cartoon character, the dog, okay? So at that time I was a student, so I was feeling very little compared to people developing codes like Prometheus, Zeus, Athena, etc., etc. Okay, I was being too humble probably, but only later, close to graduation, I realized that Pluto is also the name of a Roman god. Okay, the god of the dead and of the underworld. So after all, since all the code were named after name of gods, it was not so bad to leave the name Pluto. And so let's just say Pluto I like because it's a mythological figure shrouded in mystery.
Good answer. Any other question?
Hi, Andrea. I'm Shesha from my Inbox. So my question is there any recent planning of incorporating general relativity in this?
Oh, yes, absolutely, yes. I forgot to tell you, and that's my fault, sorry. Yes, actually, we are already doing this. We are already doing that. I should have put here, Matteo Bugli won a Marie Curie fellowship and is now a postdoc of mine for another year. He has done already 1 year and is developing a general relativistic module for the code. We have already a working 1D version, and we are extending to 2D during these days. So probably by the end of the year, we will have a working version. I'm not sure whether this will be released public until we have a stable release, but at some point definitely will. So yes, there is a plan and it is already being acted.
Thanks a lot, Andrea. That was really wonderful. And you were really well prepared. I have to say, every point that I mentioned in that thing that I prepared, you covered really, really well. Thanks a lot. We really appreciate it. But next time you have to be here.
Yes,
okay?
Yes, I promise you. But just tell me with some advance, at least 4 months in advance.
Absolutely, we'll do that. Thanks a lot.
Okay. So good luck to students, masters, PhD, and I really hope you the best for your career. Okay. Keep coding.
Good.
Bye.
Bye. Ciao.